All right, is the audio working? Can we check someone? Can you hear me? Okay. All right. Good morning, everybody. I'll be talking about conformal prediction beyond exchangeability. This is a paper by Reena Barber, Emmanuel Candace, Aditya Ramdas, and Ryan Tipshirani. And this came out fairly recently. So this was like February when the paper came out. So I'll just be going over the main algorithm and give the proofs along the way and show some experimental results that they have in the paper. Okay, so we start off with conformal prediction under exchangeability, and this is the algorithm itself. So I'll briefly go over the description and then talk about the bounds that they have for under exchangeability. So the input to the algorithm is the training data. So you have n data points that's given for you for training, and you have a test point xn plus 1. Then you have the training algorithm A, you have a non-conformity measure M, and you have significance level alpha. The training algorithm could just be any algorithm. So for classification, you can think of SVMs. For regression, you can think of a linear regression model. The non-conformity measure is basically telling you how different a point is from the points that you've already seen. So an example of that is just under least squares regression is just the L1 or the L2 loss that you incur. So the output of the algorithm would be a prediction set. And we'll show properties of the prediction set. So we start off with an empty set for the prediction set. You loop over all possible y's for the data point xn plus 1. You use your training algorithm A to learn a model mu using all the data points from x1, y1 through xn plus 1, yn plus 1. For each point, you calculate what the nonconformity measure is. So that is, again, like that. An example is just the least squares loss. And if your loss on your n plus 1th point is less than this quantile described over here, then you include it in the prediction set, otherwise you don't. And the quantile itself is defined by the, it places equal weight on each loss Ri, and the weight of the loss is 1 over n plus 1 in this case. And the level of the quantile is 1 minus alpha. And I'll show that why they have these decisions in the algorithm itself. So I said that we have this algorithm under exchangeability. So what is exchangeability? Your random variables R1 through Rn are called exchangeable if the joint probability density function f, in this case, is not dependent on the ordering of its arguments. So for any permutation pi over n, over the indices 1 to n, you have this property. So it is equal no matter how you permute the arguments of the arguments to the joint probability density function. The assumptions made under this algorithm is that the data points y1, all the data points from 1 through n plus 1 are exchangeable. So that is the first assumption. And the second assumption is that your training algorithm A is symmetric. So similar to what exchangeability does, symmetric also means that it is not dependent on the ordering of its arguments. So no matter how you pass the arguments 1 through n plus 1, you'll end up learning the same model using this training algorithm. Under these assumptions, you can show that the nonconformity scores R1 through Rn plus 1 are exchangeable. And we'll use that property to show that you can bound the probability of an error occurring. So we say that an event, or the event of an error happening is when yn+1 is not in the prediction set. That is just by definition. And that happens if and only if your non-conformity score for n+1 is greater than the quantile as defined before. So there's nothing new over here. It is just following the definitions of what we were doing in the algorithm. Then we define the set of change points, SR, as all the indices such that the non-conformity measure for that index is greater than the quantile I described before. So by definition, the sum of the weights of all the points under this set is less than equal to alpha, just because the quantile is quantile is measured up to 1 minus alpha. So we can redefine when an error happens as when n+1 is a strange point. Following that, we can say that the probability of n+1 being a strange point is the sum of sum over all I, with the probability that I belongs to the strange set. And since they're all uniform, then we weight it by 1 over n+1. And that is just through exchangeability. We can change the probability to an expectation of indicator functions. And through that, we can say that this is less than equal to alpha, as this was in the previous slide shown to be less than equal to alpha. So are there any questions over there? This is the algorithm again. I think it was fairly straightforward. And the proof is also fairly easy to follow. But if there are any questions over here.
So the predictive set is a subset of possible X values that theoretically could come after.
The subset of all Y values, which are the labels for xn+1. Yep. Yeah, so instead of returning 1 point, you return a prediction set. And you want to show that the true label lies in that prediction set with certain probability. And yeah, so we show that the probability of an error happening is less than equal to alpha. Okay, so what this paper does is gets rid of the assumptions that we made in the previous algorithm. And the two assumptions, the first assumption was that the data points are exchangeable. So they get rid of that and they introduce weights y1 through yn+1, which are in the set 0 to 1. The intuition behind the weights is that you place a higher weight on examples that you trust more than others. As an example, that if you know that certain points belong to the test distribution with higher likelihood than the others, then you place higher weights on those than the other ones. An example for that would be like if you know that your data is drifting over time, then you place higher weights on the data that you've seen most recently than the data that you've seen in the past. So you start from 0 and then you can linearly interpolate to 1 as an example. And in this case, this set yn+1 equal to 1. That is that you place highest weight on the n+1th example. So all yn+1 is greater than equal to, just disappeared. Okay. Yn+1 is greater than equal to all other weights. And then you can define the normalized weights as y tilde I, and that is just the normalized weights that we'll use later. And I'll get to how we use the weights. The second assumption was that the chaining algorithm is symmetric. We get rid of that and introduce tags, which are just these, it lies in the subspace T, and they're basically just features that you're adding to your data point. So for each data point 1 through n+1, you add a tag. And what the tag can do, it can play multiple roles depending on the task that you have at hand. So one thing it can do is it can indicate weights for weighted empirical risk minimization. So in terms of weighted least squares regression, like you can add these tags and you can have weighted losses, and you can minimize that. It can indicate the time and or the spatial location where the data point is collected, or it can just indicate the order. So you can just say that Ti is equal to I to indicate the order in which the data point is collected. So it basically depends on the task at hand, and it can change with different problem settings. And in this case, the weights and the tags are all fixed beforehand. One key modification that is made in the algorithm is that you randomly swap the n+1th data point with another one. And how do you do that? You randomly sample k from all the indices with the following multinomial distribution, where the probability of picking an index I is proportional to your weight that you've assigned to it. So you're more likely to pick the ones that you trust more, basically. Once you sample a k, you define a permutation pi k on all the indices that swaps the indices k and n+1. So if I is equal to n+1, you return k. If I is equal to k, you return n+1. So that's the only swap that you have. Otherwise, I is the same. So in this case, if k is equal to n+1, you basically get the same permutation. There's no swapping happening. Once you define this permutation, you train your algorithm using these data points now. So notice that you've introduced the tags t1 through n+1, and you've swapped the xy's when necessary. So you have pi k1 over here, pi k n+1, pi k n+1 over here. So you swap all the xy's, but you keep the tags the same. And then this is the algorithm that they get. So the changes are denoted in red over here. So the additional inputs are the normalized weights, the tags, and in terms of the algorithm, now you have an additional step of sampling k from the multinomial distribution defined earlier. Now you have mu k, which is the model that you get by training on the data points with the tags and with the permutation. And you have a new non-conformity measure, which is dependent on k, on mu k in this case. But the condition is more or less the same. So you say that you include data point yn+1 if your non-conformity measure rkn+1 is less than equal to this weighted quantile in this case now, where the weights are defined by the WIs that you had before. I'll go over why this algorithm. So with that algorithm, we know that an error occurs when rkn+1 is greater than your quantile that we had before. That is again by definition. Then we'll replace rkn+1 with infinity in the quantile itself. And you can do that because of this result over here. So for a discrete distribution f, if you have fixed support, f1 through fn, we can say that the quantile beta f is q. Then we'll replace f with a new distribution f tilde, where all the points that are larger than your quantile can be any arbitrarily large value, and your quantile still remains the same. So you're moving the mass from all the points that are larger than your quantile to arbitrarily large values, and the quantile does not change. So using that result, we replace this quantile with the quantile over here. So we replace the mass on n+1 with infinity. So we expand on this quantile over here in the next slide. So we take out the index k from the summation, and we add wk in wk delta infinity. We add and subtract it on both the sides in this term and this term. And then over here, we notice that rk n plus 1, sorry, rk n plus 1 is less than infinity, and rkk is less than infinity. And we know that wn plus 1 minus wk is greater than or equal to 0. That is because the weight that you assign to n plus 1 is the highest possible one. So that is 1 for sure. Normalized before normalization, that's 1, and wk is less than or equal to 1. So we have this inequality over here. Then we can remove remove the terms rkk over here and over here with the same weights wk, and we get that the quantile is now defined over this permuted set rk pi k, but the same weights. So ws are the same and rk pi k changes. Any questions over here? Okay, so we now say that the error happens, an error occurs when rkn plus 1 is greater than the quantile defined in the previous slide. And we can also replace rkn plus 1 with, we can replace n plus 1 with pi kk, and then we get the same quantile over here. So now we define a set of strange points for any set of nonconformity scores R as the indices where Ri is greater than the quantile as described above. Sorry, with the weights as described above, but the Ri's are changing depending on what your input is. So this is true for any nonconformity measure vector. And again, by definition, we see that the sum of the probability mass contained on the indices that are chosen is less than or equal to alpha, again, by the property of what a quantile is. So now we can say that an error occurs when k is in the set. So strange points on the conformity measures obtained over the permuted set pi k. Any questions over there? Okay, so the probability of k being in that strange set is equal to the summation over all the points when k is equal to I and I is in the set of strange points. And since we picked k independent of the data, we can just say that that is equal to the weight, wi, delta wi. And we get this inequality over here by introducing the total variation distance between rk and rk pi k. So we replace the strange points to be over rk as from the above equation, and we introduce the total variation distance. Now we know how to bound this over here. We can replace the probability with an expectation and an indicator function again, and that gives you the sum of the probability mass on the points that are in the set, and that we know is less than or equal to alpha. So we know that the probability of an error is bounded by this value. So the additional term that we got by extending this to non-exchangeable distributions is this.
So would it be a way to kind of get the weight dependence of the observation and still get some kind of valid bound?
So you can get the weights dependent on the data points, and like there's the weighted exchangeability paper that does that, and you can essentially get the total variation distance of this dependent on the weights and the tags given. This also might need to change over here. Yeah, but they don't have any works on that.
Okay.
But yeah, it makes sense to have the weights. It would make sense to have the weights dependent on the data.
Yeah, exactly. That's what it seems a kind of obvious
Right.
extension.
Okay, so this is the algorithm again. Again, the changes are highlighted in red, and there aren't too many changes that you make from exchangeability to beyond exchangeability. But if you have any questions over here. All right. So the experimental results.
Actually, I have a question. So
Yeah.
what do you lose with getting rid of the exchangeability condition?
Like you lose the
Basically this.
Okay, so that's the penalty, I guess, that you're paying.
Yeah, so if your data is exchangeable, this would be equal to 0. So this would be 0. So yeah, that is what you're losing when your data points are not exchangeable. So data points are not exchangeable plus the algorithm not being symmetric. And this is on the residuals or the non-conformity scores themselves. And then you can also say that this can be expanded to just the xi, yi's, and then permuted set. But this is stronger.
Is that for a fixed permutation set, or is that? We have the notation.
So this is fixed in the sense that you are replacing it with a certain k, but your k is a random variable. Any other questions? Is there anything online? The shot's going to be pretty short.
Okay.
Talk's going to be pretty short, sorry. Right. Okay, so experimental results. So they have toy examples and they have a example for real data, but I'll display the toy one because it's fairly easy to understand in terms of what is actually happening and how the algorithms differ. So in the toy example, they generate 2000 IID data. Your xi's are the same everywhere. So that is a 4-dimensional vector with 0 mean and identity standard covariance matrix. And your yi's are defined the same everywhere. But the only thing changing is the coefficient vector. So the coefficient vector in the first case is fixed. So that is 2, 1, 0, 0 throughout for all data points. In the second setting, which is change points, they have drastic changes in certain sections. So from 1 to 500, they have a fixed beta. From 500 to 1500, they have a fixed beta. And then for the last section, they have a fixed one. So you'll see drastic changes in the graphs as you see the betas changing. Then they have a third setting, sorry, this should be 3, of distribution drift. So they say that we start with beta 2100, and the last one would be 0021, and then all the betas in the middle are computed by linear interpolation. So the third setting is a gradual change where you have linear interpolation. The second setting is where you have very strong changes in your beta. So the distribution would be very different. So we have 3 algorithms over here. So CP plus LS is the original conformal prediction algorithm with least squares regression. Next, CP plus LS is the proposed conformal prediction algorithm with least squares regression. So there are no tags in this case. but your weights are defined as over here. So it is 1 for wn plus 1, and then it decreases exponentially. And then the third one is next CP plus WLS, which is the proposed conformal prediction algorithm with weighted least squares regression. So now you have the weights and the tags, and they, in this case, they have it set as the same. So you have, again, 1 for n plus 1, and then you have exponentially decreasing as the i's get lower. So for n equals 10 to 1,999, they run the method with training data 1 through n, and the test point n plus 1, and the desired coverage level is 0.9 in this case, in the experiment. And this is the graph that they get. So on the left-hand side is the coverage. On the right-hand side is the prediction interval widths, and you have the settings sorted by the rows. So in the IID setting, where we know that the data is exchangeable, you get more or less the same coverage for all the algorithms. And the prediction interval widths also pretty small, but, are the same, more or less the same. But the ones for the CP plus LS is slightly lower because you don't have the weights anymore. So in that case, since we have equal weightage across the whole, across all data points, then your expected sample size is higher, since you're not lowering the weights for any other data points. In setting 2, where you have these drastic changes, you can see over here that the coverage changes drastically also, like when you hit those points. And you see that next CP plus WLS recovers very quickly. And even without the tags, next CP plus LS recovers fairly quickly. But the blue one, which is CP plus LS, is fairly slow to recover and get the same coverage. And the prediction interval widths over here are also the smallest for next CP plus WLS. For CP plus LS, you can see that it keeps increasing as your distribution change. As your distribution change, it increases, and then it keeps increasing. And the last setting, where you have a gradual shift in the distribution, you see that CP plus LS also gradually lowers in the coverage, but the red one and the yellow one are fairly consistent, and they have the desired coverage. And the prediction interval widths also reflect the same thing. So the red one is fairly consistent. The blue one increases slightly, but then the yellow one is fairly high, but you get the desired coverage that you want through the yellow one. Any questions over there?
Do they talk about how to choose the weights and stuff?
They don't. So this is, they say that is an open question. In the experiments, they just use the setting where you have 1 in n plus 1 and then exponentially decrease them. But yeah, they don't talk about how to get the weights or the tags in this work.
What you raise as a question to me is that clearly, so here they pick the weight independent of data, which is not right. We know that if we knew the distribution of the test on the train, we should correct the impedance weight.
Right.
Okay? We know that if you don't have the right impedance weight, you have an approximate impedance weight. We have bonds, the paper of Lay on Candace, it's been generalized in the label sheet by Fest. Stuff, you can have some inflated confidence interval, which are function of how close your approximate weights are close to the true weight. What I conjecture is that if you were able to do what they are doing with some kind of weight dependent, data-dependent weight. If you could generalize the reasoning, I imagine you have tighter bonds. That's what, and I think it'd be really interesting actually.
Right.
Because you would say, for example, on your interesting, it's kind of positive. I do a lot of test data stuff. You want to use the information about some kind of approximate ratio, somehow.
Right.
And I would be much more, and then not use the Lee and Candace bonds, but just most likely a conjecture would be sharper what they're doing here. It seems more less brute force actually.
Yeah, in this case, so in setting 2, since there's a drastic change in the distributions, you don't see the same coverage, or you don't see consistent coverage throughout. But in setting 3, like you can see both red and yellow are consistent, and that is just because that the weights are basically like they set up this toy example to show that the weights are consistent with what the distribution should look like. But the result is pretty interesting that even without data dependent weights and tags, like you can get this coverage, and they have they bound the coverage basically, which is very interesting. But yeah, that's it. This is the reference paper, and yeah, thank you for your time.
Thank you.
It was fairly short, but
No, that's fine.
any questions?
You know, I think this thing would be the worst looking at. It seems to me a kind of to reconcile those two approaches, really, where one you use weight dependent stuff and then approximate weight dependent. I mean, there's a gap here actually, which is on top of very interesting because all these covariate or laboratory stuff, they are nice, but you never know the weight exactly. You have to estimate them.
So in this paper right now, they don't give any mechanism of estimating the weights, right? They just say
it's independent of the data.
Yeah, it's independent of the data, and they say that in the paper actually they mentioned that this would basically change to conditional distance, but also this would change because since your k is not dependent. Oh, sorry, k is not independent of the data anymore.
The toy model when it shows 0.99 to the power.
Yeah, so that was just something heuristic that they came up with there. And that reflects, again, like that reflected setting 3 very well. And that's where you see consistent coverage.
Not only be good to do that, but I think maybe it would tell you as well, because sometimes your weight estimate is going to blow up because it's the density ratio and numerically not right. So maybe it would tell you how to kind of control them so that you don't do crazy stuff for your confidence interval.
Yeah,
I think it's interesting stuff to look at.
I feel like this would, like, as I guess the experiment shows, if there's a sudden shift in the distribution, or if it's like a covariant shift situation where you have data from one distribution and data from another distribution, which is like an abrupt shift, then this would probably fail, right? Like, especially if you don't have a lot of data from the second distribution.
Right. And there's no mechanism to actually have data dependent yet. So because of that, it fail. Yeah.
Right.
On the mean reviewer, we tell you, but you don't know numerically anyway the second bit, so it's like we got in our review. But because it's Candace or the they're not gonna have that. It's different for them. Okay, I think it's really cool actually. I think there's an interesting problem actually to extend that to reconcile those two approaches. It's a really interesting research question.
Was there anything online? All right. Thank you.